Optimize. A journey through database query optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
Alright, so today we're going to continue reading along the Hertzgraphy, more like corpus of his query optimizers. So this is going to be the last one that he sort of developed in the 90s, called Cascades Query Optimizer, which again I think is still before you guys are born, but we're slowly creeping towards the 21st century. But this one's really good, and as I was saying before class, like part of the reason I had you guys read the chapter from the book is there really wasn't a complete description of what the Cascades thing actually is and actually how to implement it prior to that book. Like there's remnants of it in like the Orca paper, which you guys read later on. Microsoft people, some people are giving talks with us and other places describing it. But there really wasn't anything until this book describes how to do it, and I think it's fantastic. So, all right, before we get into that, I'm going to make some quick clarifications based on an email a student sent about maybe slight confusion about Volcano and how we're doing enforcement. And then I also want to emphasize something else too that I showed last class but didn't really clearly delineate about the Volcano optimization phases. And as he sort of brought up last lecture, Volcano is the precursor to Cascades, and Cascades is kind of like, the object-oriented version of Cascades, or sorry, of Volcano. So it's kind of important to understand what Volcano is doing, and then that'll help us understand the design decisions that they made in Cascades. All right, so in Volcano, even though it's considered a unified query optimization framework, they're still going to have these sort of separate phases of when they do logical transformations and the physical transformations. And so the first phase is called the generation phase, and that's where they're going to still do top-down search, but they're basically going to explore and explode out all of the logical expressions you could have for every single logical expression as you're going down. So basically, as you traverse down to the tree, you're going to apply all the logical rules that you can for the logical expression or operator you're looking at, and then traverse down further. So it's sort of like you're exhaustively expanding out all the possible logical expressions you could have for your query plan. So say at the very beginning here, we have a simple query that's doing a join in ABC. And for simplicity, I'm just going to say, here's a grouping of A join B followed by join C. So you would traverse down here, and there would be a rule that says, okay, I know I need to join A and B. So if I come down here, how am I going to get the values, or how am I going to get data from A and B into my query to do this join? So as you're going down, you're now bidding out these components here, right? And then you could do additional logic ordering. You could swap the order in A and B here, but we'll ignore that. But then say now you have another transformation rule that says swap the order of the join so that you join C with the output of A and B. So just swapping the order, which we can do because the swap is commutative. So again, now I'm going to do the same thing. Now I'm going to traverse down my tree, explode out all the possible variations on the logical expressions I have as I'm going down. But they have this hash table that the early version of the memo table that Cascades is going to use, where they're going to keep track of what logical expressions they've seen before. So in this case here, we saw the get on join A and B. We've seen this expression before, so we know we don't need to go down and traverse anything below this because we've already found that down, right? So we don't need to go further here. So then now again at the same level, I'm expanding out all the different ones. I need different variations of this join, and again because it's PowerPoint, I can't show everything, but again I'm just keep applying the same rules over and over again, and I'm getting more logical expressions at this level, right? And then now once I reach sort of say all possible logical rules that implied, now I enter the second phase, which they call the cost analysis phase, where now that I'm going to do a top-down search again, but I'm going to try to pick what is the best physical operator to use to implement the logical operator at each level of the tree, right? So say, just for simplicity, I'm just going to go down this side. I say, all right, well, I know I need to join A and B. Or sorry, I need to take the output of A and B and join it with C. So I'll use a hash join for that. And then now I know I got to get the data from the join A and B and from table C down below. So I'll follow these logical operators, apply rules that convert, the get A and B, get the join A and B into a hash join on A and B, and then likewise go down below and now get whatever the access method I needed to access this table. I'm not showing the arrow going down. These arrows are indicating that I'm applying a transformation here. Right? And the same thing, right? Since I need to know how I'm going to access C, say there's only one option, it's a sequential scan. So I traverse down and do that. So again, in Volcano, the key idea here is that you're going to expand out all the possible logical expressions you have in this first phase, then go back and try to figure out what the lowest cost to implement those logical expressions, those logical operators. And in Cascades, they're not going to do that. They're going to only do the expansion or the application of the rules to expand out other possible logical expressions for a given operator, a given expression on demand, right? As controlled by the rules and the promises that determine the order that the rules get applied. So you can sort of think like this is, again, it's sort of like the stratified search in that they're doing, it's not like rewriting where you're going to one format to the next. In the case of Starburst, right? They were taking a query graph model and then rewriting it into another query graph model, but you never went back and kept the other one around. This is you're sort of expanding out all the possible choices I could have ahead of time. Then you're going through in the second phase and actually then costing them. So it's unified in the sense that it's a single sort of framework that's applying all these rules to do this transformation. It's just running in two different modes, two different phases. The next thing I want to clarify is how enforcers work in Volcano, right? So again, in Volcano, enforcers are actually these virtual physical operators that get put into the query plan that are meant to guarantee or provide to ensure that whatever the output it is that's coming out of that enforcer will satisfy the properties that the query plan requires. Sort order is the most obvious one here, right? And so say we have an example here. We have a select star on a table, and we have a predicate on column A, and they have an order by on column B, right? So again, in a top-down goal-oriented search, you start with what you want the output to be, right? And say in the first phase, we're doing the generation, the transformation of all the logical operators to logical operators. So in this case here, we would inject the enforcer operator here to say an order by on column B, and then below that now, as I'm getting data out of table XXX that satisfies, with this predicate being satisfied, right? So then now on the other side, now I can start expanding out in the cost analysis phase. Now I can start applying rules that convert the root of the query plan tree into physical operators. So on one side here, I can say, oh, I know I need to do an order by on table B. Well, I have an index on B, so let me do a scan on that, followed by a filter on A. Right? I'm showing this sort of as one step, like converting that logical plan into physical plans and expression. But it could be one or more rules could do that. Right? In this case here, for this expression, it has the property that the data is going to be ordered by that TB should be XXXB on column B. So that is guaranteeing that's satisfying the property that's required by this on this for the property on the root. So the rules would not let you do an expansion or convert the logical operator into physical operator that did not provide that property. And so the enforcer is a way to allow you to still consider alternative query plans or subplans in the tree that may not actually satisfy on their own the property that you need up above, but when I do my conversion now to physical operator to a physical plan, I would know that I could convert that enforcer into a physical operator that provided it. Case for sort order, a quick sorting algorithm. So over here again, I have my order by enforcer, and then that's feeding in. It's getting input from the get logical expression on table XXX with this predicate here. So then now as I do my expansion and I convert this logical operator to the physical operator, say I'm now doing an index scan on A, then do the filter on A, and then now since this has no properties that are being satisfied, I know now when I convert this enforcer, so when I want to generate the physical plan for this expression, I know I need to convert the enforcer into a sorting algorithm that sorts on the column that I want. And then now the properties of this expression and the data coming out of it satisfies the property that the parent needs. So this will be a big distinction in between Volcano and Cascades. Volcano, they're explicit operators called enforcers. In Cascades, they're just going to be rules, like any other rule. So the problem with this one in the approach, and they say this in the Cascades paper and in the chapter you guys read, right? It's basically that they had to add a bunch of ad hoc code in the system or in the optimizer to do this like injection, and then sort of it wasn't exactly maybe entirely a rule the way other rules were written, but then when you want to do this conversion, it's kind of like this ad hoc thing. Say, oh, I know I need this property. What be satisfied? What property is it? And then there's a mapping to say, for that property, here's the physical operator you need to enforce it. So similar to how like the sort order in system R in that first query optimizer we looked at was sort of tacked on at the end based on the interesting orders. They're doing somewhat similar here, although it's not as hacky, for lack of a better term, than what system R was doing. Right, but then Cascades will have, again, treat enforcers as a first-class entity or as a rule. Okay? All right, so today I want to, again, do an overview of Cascades, go deep into what the tasks look like, the optimization that you can then apply afterwards, and then we'll finish up quickly looking at a preview of some of the other query optimizer implementations on Cascades. We'll look at the rest of the semester, so Orca and Microsoft. And we talk a little bit about Cockroach as well. All right, so as I said, this is the third query optimizer that Gert Graffy developed. And this was done after he left University of Colorado and then went to Portland State. And there's a paper in, I think, like, not like Sigmod or VDB, but like in like a IEEE conference or like a bulletin that describes what Cascades is. And that's the original Cascades paper. But then he, as far as I know, he didn't actually build a Cascades optimizer. Like in Volcano, there was a Volcano optimizer, there was a Volcano system, and there was a deployment down in Texas that actually was based upon it. Right? As far as I know, with Cascades, he wrote the paper, left Portland State, and didn't actually end up building it. But then he was on a master's thesis that came out in 1998 called Columbia. That was one of the first implementations of Cascades. But the reason why he didn't build it at Portland State is that he got bought up by Microsoft, or left Portland State to go to Microsoft in 1995, and he got hired to help build their new query optimizer based on Cascades and the Volcano parallel exchange execution stuff that we talked about in the intro class, right? So as I said, this one is the first Cascades paper in 95. But again, you can't really take this and implement it the same way you could Starburst and the System R1 or even Volcano. All right, so it's going to be a top-down approach, just like we saw in Volcano with backward chaining. It's going to do depth-first search, again, also like Volcano, but the way they're going to order the task, and I'll find that in a second, and basically what thing I need to do or the optimizer needs to do to keep exploring, expanding upon in the query plan. That they're going to maintain the order in which you need to apply those tasks in a stack. Whereas in Volcano, it's just recursion. Like I call this and call this and call this, and then as I reach the bottom of the tree and I'm applying rules, when I unroll and basically just calling return and go back up the stack. And then this one's going to be a stack is going to be a separate data structure with last in first out. They're going to apply the tasks, and there'll be some scheduling mechanism that can pick things off and figure out what to run. And it's not always going to be last in, first out. We'll see promises in a second. You actually can reorder the tasks based on how beneficial I think something's going to be. So the other thing they're going to also be able to do is the paper doesn't really talk about this, but my understanding is that they can actually do some rewriting of predicates and their expressions directly in the code without necessarily having to do like an exhaustive search. Like if you know that 1 = 1 should be true, they have a way to fire that off and do that rather quickly. right, in the very beginning. And we'll see how they do multi-stage stuff in a second. All right, so what are the key ideas in Cascades that makes it different than Volcano? So one is they are going to treat optimization tasks as sort of separate data structures or structs that kind of say, here's the thing that I need to do, rather than having this rule firing mechanism that says, okay, if I do this, then apply this change and update things. And the rule itself is kind of the keeping track of what the task it is trying to do. Where now they're going to have explicit tasks, again, as a first class component in the system. And then now you can do all the scheduling tricks you want to do to make sure things run correctly and in parallel. Instead of doing enforcers as separate sort of virtual plan nodes or operators, they're going to use rules to figure these out. We'll look at that more in a second. They'll have this notion of a promise that's similar to that sort of cost adjustment we saw in Exodus, where they have a way to say, I think this thing's going to be a bigger win for me, so give this rule a higher priority and try to apply it sooner, maybe instead of later, compared to others. And then the other big one is that, again, this unified representation of all the rules and all the operators, no matter whether you're operating on a logical operator or a physical operator. In some systems, you can throw predicates in there as well, the predicate trees. All of that is in a single search engine with a single representation of here's what a rule is and here's what an operator is. Again, in the Volcano paper, it's not really kind of clear, but like basically they have like, here's the API you would write rules for logical operators, and here's an API you would write for rules for physical operators. And then there were sort of separate mechanisms or executors, if you will, that would then fire off those different rules, and you couldn't intermingle them. Whereas in Cascades, they're going to say, sometimes I actually want to do maybe some logical expansions first, or physical expansion first, before I do some other logical ones. And they can intermix these things and then try to guide the search to find the things that are more beneficial more quickly. All right, so now we're going to go in more detail what these expressions are, and then that's going to feed into groups, and that's sort of the scope in which we're going to examine the query plan tree as we're going down. And it's a way to compress the representation of what our query plan looks like through these concepts of groups that are client expressions, so that we don't have to have all this redundant information in the memo table as we're going down, and then have a mechanism to figure out, are these things actually equivalent or not, over and over again. We're going to combine these things together in groups so that within sort of a single location in our program or in the optimizer implementation, we can find all the things that we know are the same. So expression, we said this before, is going to be some set of operations with zero more input expressions. It could be a combination of physical expressions or logical expressions, right? And then we're going to have a mechanism in our system to be able to figure out whether two expressions are equivalent. And that means both logical expressions are equivalent, but also our physical expressions equivalent with logical expressions, right? We need to go both ways, right? In Volcano, as far as I know, since the logical stuff was kept separate from the physical stuff, they only had to compare logical with logical or physical with physical. In this world, we got to know that across both lines are things equivalent. Right? This is going to allow us to apply all the transformations we'll see next week to do, rely on commutativity, associativity to know when we reorder things and things are okay. And then the container we're going to use to represent equivalent expressions is going to be called a group. And a group's going to have some output that's defined as a logical expression defining what's coming out of it. It can have properties that specify what the data that it's going to emit is going to look like, sort order and all the things we talked about before. And then they're going to have a sort of a unordered list of all the logical expressions inside this that are equivalent. I shouldn't say unordered. This could be ordered if you wanted to. It doesn't matter. But here's all the logical expressions that are equivalent to produce the output that I expect for this group. And likewise, here's all the physical expressions that are equivalent that will produce the output specified by the group. So this overall container here, this is considered the group, and then the sort of the two pieces here, these are just again all the equivalent expressions. Like A join B join C, that's equivalent to B join G, B join C join A, right? And our output is defined even more high level to say, here's A, B, and C coming out. I'm not even specifying the order of anything. Right, so this output sort of looks like the QGM or the query graph model stuff, where it's like, I'm not saying this is relational calculus, but like it's a higher level than these relational algebra definitions of what the expressions are, because again, I'm not specifying what the order is. I'm just saying here's some output coming out that it will be the logical representation of A join B join C. All right, so what is this thing again? So again, this is going to be a placeholder for us. As I said, that's going to what is the logical output that I expect for some expression or sub-expression. So now we're going to use this to compress down how much data we actually have to store, or how many redundant expressions we're going to store for a given group. Because now, instead of saying within our logical expressions or even our physical expressions, for the things that are below me in the query plan, I don't know how that's actually going to be executed. But in this higher level part of the query plan tree made me looking at a given group, I don't care. So going back here, right? So here I have logical expression A join B, followed by take the output of that and then join C. But I don't really want to keep all possible combinations of how I want to join A and B at the logical level. I'm just going to say I have this representation here that says, hey, there's A, B. Down below me in the query plan, they're going to be joined together. I'm not going to tell you what order. I don't care what order at this point here. But just know that there's a placeholder here that says there's some group below that's going to tell me how to do this join here. Likewise, on the physical expression, same thing, right? So I have the join order being specified is I'm going to join A and B. Don't know how. That's below me. Then I'm going to do a cert merge join on C with the output of C. And again, the placeholder here with the curly braces is just saying down below me, you're going to get C. I don't know how, but you don't need to record all possible combinations of that. And that was one of the problems that going back to Exodus, where they were doing this. They were just storing everything over and over again redundantly. Is that clear? Yes.
So groups tend to have an input. Their inputs are other groups.
His question is, groups can have inputs. I think I say that here. I don't say that. Well, an expression can have, right? Expression can have 0 more inputs, right? And so the group is just a collection of expressions that produces output. So implicitly by that, they have inputs, 0 or more, right? If you're a sequential scan at the bottom, typically you're gonna have no inputs. Joins up above, they'll have more. And for simplicity, we're just gonna assume that we're doing, binary, unary groups that is either 1 input or 2 inputs or 0 inputs. But if you're doing multi-joins, which we're not going to cover this semester, you can have 3 or more. All right. So now what do our rules look like? Well, the rules are to be just as we saw in Volcano last class and before in other systems. We're going to have the distinction between the transformation rules and implementation rules. Transformation rules is going from logical to logical. So a logical expression to another logical expression. And the implementation rule is going to be logical to physical. And then each rule is going to be represented by a pair of attributes. I think in the implementation, they talk about it's a function that you call where you pass in, here's the expression that I'm looking at, and maybe other context information. But it's just a way to say, is there something in my query plan that going to match based on some pattern? And if yes, then there's some rule that's going to say, here's the change I want you to make to either a logical expression or a physical expression to produce some variation of the query plan. Right? So again, we're going to go in way more details in different kind of transformations in the next class, but here's a more complicated rule maybe seen before. Say we have now, we're trying to find when we have 2 joins, and then we want to figure out how to optimize them, right? And then now we have this notion of groups in our rules. Again, they're just placeholders to say there's something below me in this equijoin that I'm doing here. I don't know how I'm getting what it's doing, but I don't care. I think it's like a wild card. Say it doesn't matter what's down there, but I know I have sort of this structure in my rule that I want to match on. So then now if my query plan comes along and it matches on this, right? So now I could have a logical transformation that flips the left to the right. So we're just on the root one here, we're just moving the A to stay on the one side of the joint and moving B to the other side. Or I could have an implementation rule that converts the the two expressions here, the two logical expressions to do joins into sort merge join or hash join or whatever you want. Right? We'll see this in a second. We also need to maintain now basically a bitmap or additional metadata to keep track of, like, have I applied this rule as I sort of go down this path in the search tree, because I don't want to then do the reverse and just get stuck in an infinite loop over and over again of doing the same thing. Right? In Volcano, I think they had explicit rules. They'd inject things to avoid that. In Cascades, they talk about there's like a bitmap to keep track of these transformations. All right, so now, again, the forcers are just going to be rules. And again, it's a way to guarantee that the data coming up from an input from your group is going to be have the properties that you need, right? So we go back to that simple query we had before, right? Now, instead of having an enforcer plan node in my query plan like I had in Volcano, I'm just going to keep track of, have a rule and say, am I allowed to do the transformation I'm allowed to do the transformation into this other form, to this other expression or group down below me, if that will produce the property that I care about. So rather than sort of having rules based on the enforcers, again, not exactly written the same way you would write other rules, but having additional logic to figure out, is this enforcer going to give me the data I want? It's just another rule to say, when I do a transformation from a logical form to a physical form, I won't do it unless the property I need is going to be guaranteed. Right? So if there was just a sequential scan here, it wouldn't allow you to do the conversion of the sort of the get logical operator into a sequential scan physical operator, because the sequential scan is not going to be sorted. So in the same way that there's rules being checking for other things like commutativity rules and all the other things we care about in our in relational form, relational query plans, property is just another one. And so it's not treated any differently. It's just another rule attribute that we can check and do lookup based on. So that idea, again, it seems kind of obvious now. I don't know, it was the 90s or whatever. Like to me, that this is the right way to do this. All right, so now we're going to talk about how we're going to execute the actual process of doing the search. And so Cascades introduces this notion of a task, which is just going to be they sort of use the term fine-grained unit of work that can be executed by the query optimizer during the search process or the planning process that will apply some change to the database system, right? Or sorry, apply some change to the query plan. And the idea is that by breaking down the optimizations into smaller pieces that ideally are independent, we're allowing the query optimizer to learn on its own what the best way to actually apply them, the order to actually apply them, right? Again, we saw this in Volcano, which was, again, it was sort of a rebuke of the approach done in Starburst, where they were saying, oh yeah, you can combine rules together and do a bunch of complicated things. In Cascades and Volcano, they're saying, no, you want these things to be sort of small pieces of work that do some transformation, throw them all into this queue, and then we'll figure out the right way to order them. Now, in the case of Microsoft, there's a subsection in the chapter you guys read where they talk about, oh, you can do multi-stage or macro optimizations, which goes against, again, the original ethos or the design decisions of Cascades. But again, if you're not letting any random programmer work in your query optimizer, maybe that's still okay. All right, so by default, again, in the original implementation, it's just a stack where you're choosing what the next thing to execute by whatever so in the order that they naturally appear in the implementation. But you can do something more sophisticated now and also keep track of what is called a promise, which is a way to allow you to customize the order in which these tasks are going to be executed or the rules are going to be applied. And in the case of Exodus, they had, again, that notion of the expected cost factor. The idea there was similar to a promise here, but it's inherently tied to cost, the cost or objective function that you're trying to optimize the query plan for. Whereas in this notion of a promise, it's actually independent of the cost. There's certainly some times where you do want to consider cost, because that may be the right thing to do. And choosing the right promises for tasks as you go along dynamically could steer you towards a better cost. But the calculation of itself is not directly tied to the cost function. Because again, when you're doing logical optimizations, there may not be any cost in the very beginning, right? Because you haven't figured out how you're going to scan a table, for example. So like there is no notion of a cost for a logical operator. But so you need promise to then figure out what could be a good idea, good decision to make. So again, the promise is just going to be an estimated benefit of a move on a given expression relative to the other tasks that the query optimizer could choose at that point. So let's say we have a simple query like this. We're going to join A and B, and we're keeping track of the sort of the relational properties of like what's the cardinality of each of these individual operators. Again, it's not a cost; it's just an estimate of how much data is coming out of it, right? So I could have again two transformation rules like we had before, where I could convert the logical operator to the join to do a hash join, or I could do a swap of the join order, right? Have B be the outer table versus A be the inner table, right? So again, without a promise, it would just be almost random. However I implemented the system, right, in the order in which these rules get applied, that's how things would get pushed onto the stack. Maybe I would execute them, right? But if we're aware of somehow just getting through by examining what the current state of the expression we're trying to optimize for, if we are aware of something about it, then we can make this decision which ones actually would be better. So in this case here, since we know the cardinalities of the get operators on the two tables, right? We see that the bigger one on A is 100 million tuples. B is the smaller table; it's at 10,000 tuples, right? So that's just textbook query optimization from the intro class. You always want the smaller table to be the outer table. And so you can then have a way to compute the promises based on these properties such that you'll give a higher priority to doing the swap, because I'd rather explore that side of the query plan with B being the outer table and A being the inner table, rather than messing around with this, the physical operator of joining A followed by B, right? A with B, right? So again, I didn't actually compute the cost of this logical plan. The promise is somehow some magic function that I have to implement in my query optimizer. The promise is telling me, hey, this thing is probably a better rule to apply. Go ahead and do this before you do this other one. Because then now I could, say there's only two tables in here. We'll basically do an exhaustive search, but I would end up exploring this logical expression here, then look at converting the logical operator of B join A, convert that to a hash join or assert merge join S loop, whatever join implementations I have. Then I'm going to get a cost for that. Then now, if I then come back and now apply this rule to convert the logical operator A join B into a physical operator, I would then get now a potential cost estimate of how, what the rest of the query plan is going to look like below me. But I would see that I've already got the physical. I already figured out what the cost of the physical join of B join A, and that's going to be less than anything I'm ever going to do on this side here. So I don't need to explore anything else below me. So again, it's not going to guarantee that we're going to speed up the search. Like the complexity is still a mess, right? We still have to deal with that. But in practice, right, we're going to land on a better query plan more quickly. And then, of course, it depends on how good your cardinality estimates are, right? If there's no predicates on A and B, it's just the number of tuples. The catalog will have that. But if you're now trying to estimate the predicate or the selectivity of a predicate, and you don't have good statistics, the promise may actually end up being wrong. So logically, the implementation may be correct. The data being fed into the function that computes the promise may just be wrong. But again, we're not there yet. We'll cover that later in the semester. So is this clear? Okay, it's pretty simple. It's pretty clever. And obviously, you can expand this and do more sophisticated things. All right, so now we want to talk about what these tasks actually are. And again, what I was saying before is like some of this is in a little bit of the Columbia paper, the Columbia master thesis from that student in the 1990s. But like the Orca paper, and like the complete definition of what these all doing in Cascades, there wasn't really anything out there until this book was written. So there's sort of three groups of the different tasks you could have. So the first are just doing optimizations of either a group or expression to generate the best physical plan for any one specific thing for either one target. And then the explore options are going to be looking at the group or looking at expression and applying all the logical transformations that you would have to generate more expressions or more groups, right? And the way you would generate more of them is by applying rules for taking some input expression and a rule, apply it, and then that's going to produce one or more outputs that you can then either feed back into to logical expressions or groups you need to explore later on, or I can then convert them into well, at this point I have them in a physical form, but I know that the group that I'm looking at, expression I'm looking at, has children down below that I haven't optimized. Then I recursively call down and optimize them. So being hand wavy doesn't make any sense, so I'm just go through the flow diagram. So at the very beginning, we have a SQL query. Assume again, out of the parser, we would generate in the binary, we would generate the sort of the top level group. Again, it's top down goal oriented search. So the top level is going to be, here's the expected output that I need for this query plan to find it in the root of the group. So for the root group of the query plan, but there's nothing below you at that point. Then now in the first step, you got to then say, okay, well, I have a bunch of these logical expressions. I don't have any physical expressions at this point. I have logical expressions in my root group. Let me go ahead and explore it by applying all the logical transformations that I may have to then generate more logical expressions within my group, right? Sometimes some of these could actually then also be further optimized within the expressions within the group to generate more the physical plans for the things that I have in my group at the top. Like if it's select star from table without any predicates, or select one, something really simple, then you don't need to go traverse down. You would then immediately call this thing and generate all the physical expressions you need. And then explore group is going to do more expansion, creating more expressions within my group. And then I want to do exploration of those and expanding out the logical expressions within my group. But then some of those I'll feed back into that I'll generate more groups. I want to explore those further. And then in some case here, I may do some optimizations on the logical expressions, converting them to physical expressions that also generate other logical expressions, or new group, and I want to explore them further. While this is all going, basically, the way you're going to do the actual conversion from the logical to logical and logical to physical is actually applying the rules. And there's a feedback loop again where if I apply a rule, I may generate more expressions. I want to do further exploration. Or now if I know that I've exhausted everything I want to look at maybe at this level, and I want to go further down into the query plan, I'll look at the subgroups, groups below me, then I do optimize inputs, which then just can call itself over again, but then starts with the process in the next stage. So I'm being kind of hand-wavy here. We'll look at an example in a second. But basically the idea is that you're recursively applying rules on your group over and over again to keep expanding it out. And then at some point, based on the promises, you may decide, oh, I actually want to go down and start looking at things below me because I'm not, applying more rules that the group I'm looking at are not providing any more sufficient information. All right. So as I said, there's be this stack where we keep putting tasks on to perform actions on the groups or the expressions I'm looking at. And the idea of this stack is powerful because now it's this centralized work queue that's independent of where where sort of like the execution thread, your search thread, is actually located in the query plan, right? Under Volcano, the order in which you would actually apply transformations and explore things mean, sort of defined by wherever the program counter is in the code and going down into the data structure. But now I could have a sort of a separate work queue where I keep putting tasks on, and then my worker thread can just pull things off, and it can, in theory, start jumping around to different locations in the query plan without having to go in the exact order that May would define under doing, like, recursion-based programming. So now I still need to make sure that I follow the order of dependencies in my tasks. Like if I have to resolve things at the very top before I can jump to anything below in the query plan, because those groups may not have been materialized yet. So I think I have to guarantee those things get followed. But now potentially within a single group, I could have, could go down one side of the query plan and another side of the query plan and sort of ping pong back and forth without having to do exhaustive search down in either one of them. If you just do, last in, first out, then you get that same sort of property of the recursive calls that you saw in Volcano. But if I wanted to use promises and do different kind of more sophisticated reordering, you could do that. It's the 90s, so computers weren't as powerful as they were now. So they make a big deal that in the case of Volcano, because it's just recursive calls down into the query plan, that you would overflow the stack at some point and you run out of memory, right? But now if your task queue is a separate data structure, that just lives on the heap where you have more memory. All right, so the next thing to discuss is the memo table. And again, this is going to be a separate data structure where we're going to keep track of all the things we've explored for in our query plan. And we're also now going to use that to keep track of what's the best physical operator we've seen for any sort of expression or group in our query plan, right? And how you actually implement the memo table depends on what you want to do. In the case of CockroachDB, as far as I know, they have a separate hash table on the side. They maintain the memo table. In the case of SQL Server, my understanding is the groups themselves maintain the memo table information on their own. And so implicitly, the memo table is just embedded inside of the groups, and you maintain the group data structure of the tree, right? So I think the original Cascades paper talks about being about a graph data structure, but as far as I know, most people just use a hash table, right? So again, it's a global view of what the optimizer's progress is as it's optimizing a query. So we keep track of all the transformations we've done from logical to physical, and so we don't repeatedly do the same thing over again. Likewise, if we see that we're generating a new group from some task explodes out now, expands the expression that generates a new group. If that group's output already exists in our query plan, in our memo table, then we know we don't need to explore it further. All right, this is useful if, for like if you have subqueries that are basically doing the same thing, instead of treating them as each independently and optimizing them individually, if you see that you've already seen that sort of subquery expression or group in the memo table, you don't have to expand it further. They also keep track of all the properties and the costs as you go down. And then the paper talks about they can maintain a bitmap that keeps track of, have I applied this rule to this group before? If no, then go ahead and apply it. But if yes, because I see it in my bitmap, then don't do it, because again, you're trying to avoid wasteful computations. So this is not specific to Cascades. Volcano would have the same property as well, and likewise with Starburst and System R. But it's this idea of Bellman's principle of optimality, and it basically just says that if I have a subplan in my query plan tree, and that subplan is the optimal subplan I could possibly have for that that portion of the query plan, then by definition, the optimal plan will have to include that subplan, because otherwise the global optimal would not be the global optimal. Right? Sort of tautology is saying like the subplan is optimal. Sorry, if the global plan is optimal, then every subplan within that global plan has to be optimal. So what this matters for us is that as we're traversing down and expanding our groups in the search tree process, if we have some global cost that we've calculated for the, say, the best query plan we've seen before, and if now we come upon a group that when we calculate its cost, it causes the sort of the current materialization of the query plan we're dealing with right now, if that cost now goes above the best cost we've ever seen before, we know we don't need to consider anything further in it. It's just a way to explain how the branch bound property is going to work. So basically, if we see a subtree and we're at the root of it, before we traverse down to it, and at this point we have some estimated cost, and that cost puts us at an overall cost that's greater than the best cost we've seen so far, we can just ignore everything below it. There isn't going to be some weird curve where like we go into some valley and then poof, all of a sudden we end up with the optimal plan, right? It just doesn't work that way. Things are going to go linearly. All right, so let's look at a simple example here and see how the search occurs. I'm not going to define the task we're going to do. I'm just going to sort of say how we do the search and then what's going to go in the memo table and how we populate the different groups. So say this is the query we had before. We want to join A, B, and C. In the very beginning, all we have is this group here that the binder is going to give us when we come out from that first stage. So there's no logical expressions and no physical expressions. The only thing we have is we know our output needs to be A, B, C joined together. So the first rule we'll apply will basically say, what are the different kind of logical join orderings I could have for to produce the output that I would need. So say the first one is going to be A join B and take the output of that and then join C. And again, I have these placeholders in my logical expression with the curly braces that are saying, I don't know how I'm joining A and B, and I don't know how I'm accessing C, but there's a placeholder there, and I know I'm going to go down below and look at groups that will provide me the output that I need to then fill in for this logical expression. And so say that again, based on the promises, we would say, well, we'd rather explore the how we're going to join A and B rather than just iterate or enumerate all possible different kind of join orderings for this point in the tree, right? Because again, with logical expressions, there's no cost at this point. So like I can expand them out like in Volcano, but it actually doesn't help me anyway, right? I kind of want to get a first cost of something. Like I want to get at least an initial plan. It's probably not going to be the best plan, but at least I'll get something, get a cost for that, and then that's going to help me do the pruning I would need. Again, in Volcano, you would do all possible permutations of A join B join C at the very, very beginning before you traverse any down below anywhere else. All right, so now we have a group below this, and this is connected together based on the placeholder we have in the first group. And this group is going to produce the output of A join B. And same thing, I can then apply a logical rule that then generate. I'm going to take the output of some group that's going to be the values of A, the tuples of A, and I'll join that with some group down below me that's going to give me the tuples of B. Same thing. Rather than exploding this out, looking at B join A, I'm going to traverse down now, get to a root in my query plan, and in this group is going to produce the output of A, and the only logical expression I have is get A, right? Give me tuples A, nothing there. So, and then now I'm going to apply rules that can then convert the logical expression of get A into the two physical expressions I could possibly have, right? Do a sequential scan on A or some index scan on A. And then now at this point here, because I have physical expressions and they don't have any inputs, like there's nothing feeding into them. It's like it's the base access method that's going to access the table either through an index or through a sequential scan. I can now cost these and choose which one of these is actually going to be better, right? And say that this index is for whatever reason is not a good idea, but the sequential scan is a better idea. So I'm going to choose now that the sequential scan is the best physical expression for this group at this point in my search. And it's going to have a cost of 10. Again, we'll cover how we compute those costs later on. Just assume it's 10. But then now in my memo table for group A, right, and as we see in the first column, I'm going to keep track of the best physical expression that generated the data, or generated the data I need to produce the output that this group is required to generate. I'm going to keep track that I chose the sequential scan and has a cost of 10. So then now I traverse back up into this group here, And now I'm going to look down on the other side of the join. I want to do the same thing. What's the best expression I can get, or what's the explore what's the best favorite expression for the group that's going to produce the tuples of B. Same thing. I play in the first step. I get a logical rule that just says, well, you want it B, get B. Like that's the logical operator. And then I have another apply the implementation rule that says you can either sequential scan on B or index scan on B. And then say again, the sequential scan is better, has a cost of 20. I update my memo table and say for the group that produces the output of B, the best physical expression is sequential scan on B and has a cost of 20. So then now I pop up here. And at this point, I know that I've explored below me down on how to get A and B. So now, again, based on the promises, I could say, well, rather than maybe look at B join A, maybe I want to look at the what physical algorithm, so physical join algorithm I want to use. So your promise could do that, or in this case here, if I do actually just do the swap, well, that's cheap to do because it's just a logical expression. So now all I need to do is say, okay, well, now I have this new logical expression I want to evaluate. I need to get the tuples of B, but I've already done that. I've already gone down below, right? And I can look up at my memo table now and say, oh, I've already got the best physical expression for A and B. So you actually don't need to do the exploration, right? You're done. Right? The memo table gives you that to avoid the redundant computation, right? So we just ignore that, and instead we're going to do the implementation rules, where I'm going to replace now the logical join operator with actually what is the physical algorithm I want to use. So I can do a nested loop join, hash join for A join B or B join A, and so forth, right? And now for all of these, I can then now start costing them. Because I know what the cost of the inputs are, you'll have some approximation of what the cardinalities are, how many tuples are coming up, and then now you just run your textbook join cost calculation based on whatever join algorithm you're actually using. And things we covered in the intro class, in the most simple form. And then now we can pick which of these join algorithms is going to be the most efficient, and then the cost of this group now is going to be whatever the cost of the physical operator we're implementing here, so the cost of the join, plus the cost of getting the data up into us from down below. And we put that now in our memo table. Then now I bounce back up to the top. Now I want to look at how to access C. Same thing. I would look at logical expression get A. I want to do either sequential scan or index scan. Say the index scan is now cheaper, right? And then now that gets a cost of 5. I populate that in my memo table, and then now I can then compute the total cost of this query plan. Now it may not be the optimal, but say before I explore the other join orders, but at least at this point here, when I have this and I feed that back up, I have a physical plan I can execute, and I have a cost. So then now maybe I want to then fire off rules that do more further exploration in the join orders, in the join algorithms, and so forth, to maybe find some obscure plan that could compute a lower cost for me. But at least at this point, I know if I time out and I can't do any more exploration, then I have an actual physical plan I can run. Yes?
So we know that the sequence scan is the cheapest for groups like A and B, but what if that output A and B had to have a sorted property on it? Would it still pick so that we're sorting on something table in A, there's an order by?
Mm-hmm. So your question is,
the index scan would then be cheaper, but would you see that in that A B group?
So going back here, so say there's a property where A I had to be sorted on A, right? So when I pop down here, say that the index scan on A satisfies that sort property, right? So what would happen is you wouldn't even be allowed to consider the sequential scan because the metadata about I need data to be coming into me to be sorted, right? you wouldn't maybe necessarily have, so we'd start at the top, right? Because the output has to be sorted, right? And that would sort of propagate down. And this would basically say that, like, again, like these enforcement rules will say, do not do the expansion of get A into sequential scan A, because if it's not clustered on the thing I need to be sorted on, it won't satisfy that property. So it wouldn't even be expanded out as a physical expression you would even consider.
Okay. So if we were to like use, it would have to like spit out another logical expression with like a sort expression in there in order to be considered.
So yeah, so how would it work if I did want to do a sequential scan? How would I still do the sequential scan and then inject like an order by or a quick sort or whatever, right? That would just be another rule. You could say, like, okay, if you do a sequential scan, if you do want to do a sequential scan, you would actually create another group to do the order by that then links down below the group that was doing the lookup on B, right? But then now you would have this thing where like you could have like the output at A could go to the input at A to get into this thing could go to the order by one, or could go to the sort of base one.
Okay.
Other questions? And again, when you apply the rules, they may produce other expressions. They may produce other groups, and then this thing is like there's linking occurring. I'm showing the lines here, but it's really like the memo table could keeping track of like, okay, here's for the output you want, like A, you need table A. Here's all the groups that we've seen so far that can produce that for you. And you're sort of stitching together what the path is through the query plan. And it may be different from one sort of incarnation versus another. But you're keeping track of, you don't delete groups, right? You just keep track of everything. And that, again, that's different than we saw in the query graph model when they were doing rewriting, because when they went from one query graph model to another one in Starburst, they threw away the old one, right? Because it was a sort of one-way transformation. In this world, you're keeping track of everything, which in Volcano, that was sucked, because you would keep track of things you may never even got around exploring. Where in this case here, I don't materialize a group that I want to keep track of in my system unless I've actually, I'm going to go ahead and explore it. Okay. So, all right. So, as I said before, the promises allow us to target more potentially beneficial transformations more quickly in the search process. Again, and it's decoupled from the cost or objective function in a way that Exodus wasn't, right? And so that's nice, but we're going to be able to use that promise mechanism to sort of force or hand guide or guide the sort of the search mechanism to consider transformations that we think are being more beneficial more quickly, right? It's another way to do the Starburst rewriting. If you set the cost to, if you set the promise to something to infinity, like the higher promise means that it will be chosen more likely than others. If you set a bunch of things to infinity, then like those things will get fired right away, and that's equivalent to the Starburst. Like, here's the rules I always want to apply in the very beginning. But so that's nice and dandy. But the overall flexible nature, the way the system is actually engineered and designed, is going to open up other optimizations that weren't easily done in the other systems, that again are not going to change the asymptotic complexity of the search algorithm. But again, in practice, in the actual implementation itself, it'll allow us to potentially reduce search times, the amount of time it takes to find good query plans. So the first optimization, this comes from the Microsoft book. I don't think the Cascades paper talks about this. I don't remember talking about this. Was again as I just said before, as we do the exploration of the groups in our query plan, we keep track of all the groups that we've seen before. But there may be some cases of I know I'm always going to want to apply some optimization. So don't keep it around. Basically, do the same thing Starburst was doing. Like I knew I always wanted to do predicate pushdown. So why keep the old query plan, the old query graph model that didn't do the predicate pushdown? Because that's just wasting space, maintaining state I don't need about. So in SQL Server, they have a way to specify that for this rule, when you apply the transformation, delete the old one. And then you keep tracking it in the bitmap. Like have you applied this transformation before to avoid like reversal going back to the previous form. So again, this is just an engineering optimization. It's not going to make the thing run faster. It's just a way to reduce the amount of resources the actual implementation actually needs. The other type of sort of rule that goes beyond the original Cascades description is this idea of macro rules. And this is what I was saying before, where it's it's Microsoft's optimization that allows you to do multi-stage transformations within a single rule, rather than as what Volcano prescribed was you have all these independent transformations, you throw them in the mix, and then the algorithm will just sort of find them. They're saying, no, there's certain things you always want to do one after another, so go ahead and define a macro rule that can do that, and that reduces the complexity or the number of transformation rules the algorithm has to consider, and it can run more efficiently. Again, there's no analysis of whether how much this actually helps. They just say this is what they're doing in SQL Server. And the last one that's super important, but we're not going to go too much in detail right now because we'll cover this in a whole 2 lectures on this in 16 and 17, is because now I'm not relying on the whatever thread that's traversing my query plan to keep track of like where I am in that query plan, because I have this separate dedicated task queue, that now I could have multiple worker threads do the search optimization in parallel. So what happens is in the very beginning, because again, as I showed before, like you start off with like there's nothing, you just have a single group, right? And then you sort of build out the group as you go down. The very beginning, it's basically going to be single threaded. There's no magic to make that parallel. But then now, as you start expanding out the expressions you have, you could have separate threads exploring down different branches of the tree. The memo table is keeping track of the global state of the system. So now, anytime you update that thing and you know what the best cost you've seen so far. So the threads can check that to see whether they need to prune whatever branch they're looking at, right? And of course, you have to make sure that whatever dependencies you have between tasks, like that's still guaranteed. You don't want to be optimizing things below the tree before you do anything up above. But now again, you could have multiple threads do your search in parallel. So as far as I know, the only implementation that actually does multi-threaded cascades is Orca from Greenplum, which we'll do a whole lecture on that later in the semester, and I'll mention that in a second. But the SQL Server one, as far as I know, is single-threaded. The Cockroach DB one, it's open source, you can look at it, that's single-threaded. Calcite's not Cascades, but that's single-threaded. So yes, this makes it, with the task queue and with Cascades, you could do a parallel search, but most people actually don't do it. It's still it's easier to do than certainly Volcano and Exodus, and potentially I think also Starburst as well. But on the engineering side, it's still challenging. I suspect the reason because SQL Server doesn't do it because in the 90s when they started building their Cascades optimizer, right, that was like the Pentium 4 era, right? Maybe even earlier than that. Right? You had a single CPU, it had a single thread. It wasn't until like 2005, 2004, with like Intel's in the Halo architecture where they started throwing a ton more cores. Sun had this Niagara thing, right? Like the idea that you have a multi-core CPU it's an old idea, but it didn't actually become more mainstream in the actual commercial world until the 2000s. And so to go back and retrofit an existing code base that's already running production, you're making billions of dollars on it, to go rewrite that and make that parallel is probably a risk they weren't willing to take. Again, we'll cover this in more detail in a few weeks for both the top-down and the bottom-up search. All right, so as I said, there wasn't a sort of single code base that existed that said this is the Cascades optimizer implementation, right? The SQL Server one is what he went off and helped design and build at Microsoft. There was a couple other some projects in the 90s. So Columbia we already mentioned, where Gertz Graffi was on the thesis committee. There was one out of Wisconsin called Op++, which I think was written by Jake Nesh's roommate when he was in grad school. Greenplum we've talked about, we'll mention again in a second. And then this is what we're trying to build at CMU and OpD. The first implementation was more or less Volcano, and then we threw it away. We're going Cascades now. And so there's a bunch of other commercial implementations. Tandem nonstop SQL, there's a paper in the 90s that describes what they're doing. This is the parallel database that Jim Gray helped build after he left after he left IBM. So he left IBM in the late 70s, early 80s, and he had a non-compete clause where he couldn't go work on another database system. So he went to this company called Tandem. They had these things called nonstop servers. Think of like super redundant parallel hardware, right? They had like, 2 CPUs or 3 CPUs doing the same computation in case one of them failed, like space shuttle kind of stuff, right? But for like banks and high frequency trading. But in the 80s, they ended up building a parallel distributed database system called Nonstop SQL. And Jim Gray, because non-compete was over, he worked on that. So they built a Cascades optimizer. Clustrix was a startup in the 2000s, came out of AOL. They got bought by MariaDB, and it's renamed to like Expand SQL. It's not called Clustrix anymore. It's called Expand SQL or something stupid. But their documentation mentions that they have a Cascades optimizer. They don't say how they implement it. It was never open source. CockroachDB, we mentioned, their Cascades optimizer is in single-threaded, written in Go by one of Snowbaker's former PhD students. Snowflake has a Cascades optimizer. What they're doing, and Databricks is sort of in the same thing, where they actually don't do a full transformation of the query plan because they're trying to run on data lakes where you may have incorrect statistics or no statistics. So they actually try to defer certain optimization decisions until actually runtime. We'll cover this kind of adaptivity stuff later in the semester as well. So it's Cascades, but then it's sort of, you still end up with a complete physical query plan you can execute, but there's like placeholders for certain things. So they may make decisions and change it later on. All right, so the SQL Server one is super interesting. Again, actually going back here. So for the SQL Server, CockroachDB, Snowflake, Databricks, and I think Orca as well. These links here will take you actually to YouTube videos, because we've had all these people come give talks for us in the seminar series for a couple times. Of all these, the SQL Server one is probably one of the best talks I've ever seen in my life. In previous years of 721, I didn't, because the Cascades paper was not, you can read it, it doesn't help you. The assigned reading was watching this video, because it's amazing. They go to a bunch of different things that I'll talk about in a second. So I highly recommend that. Because again, they're not going to really describe the algorithm. They're going to talk about like how they've contorted Cascades to fit with the sort of engineering priorities that they cared about. And again, some of the optimizations we'll see in chapter 5, and some of the things that they talked about in chapter 2 you guys read. Actually, chapter 4, and then things you read in chapter 2. They mentioned like SQL Server stuff, but that talks about all sorts of crazy things. It's amazing. All right, so SQL Server had the first Cascades implementation, started in 1995. And there was a single code base in SQL Server that was Cascades. And then because it was such a fantastic query optimizer, as Microsoft put out different data products over the years, they've forked the code and have made modifications for like the data warehouse version or like other internal data systems that they built. Right? They're all going to be sort of using the same Cascades optimizer. The paper we'll read at the very end of the semester is about their unified query optimizer, where they basically, instead of having all these different forks, they all merge it back into a single code base. And then they have the different rules that are specific to the different systems they need to support, which I think is obviously a good idea. Everything's in C++. There's no DSL. Yeah, the paper didn't really, the book didn't really talk about that. But in the original Cascades paper, they talk about instead of writing C or C++ code for your rules, you would write them in this high-level language, the DSL, which then would get compiled down into C or C++. Cockroach does this in somewhat, but Microsoft does not. Everything's procedural code, right? Everything is all procedural. So what they're going to do is apply the transformations in multiple stages based on the complexity of the query. So the idea, and again, this is going to smell a little bit like Starburst, but I said before, like, oh, the unified search was the stratified search. Even though Microsoft SQL Server is Cascades, they're going to do this multi-stage thing, and that kind of smells like what Starburst was doing, where there's transformations you always want to apply, maybe not even without a cost model, but that's going to set you up so that when you do the cost-based search, you find good plans more quickly, right? And unlike what we saw maybe in Volcano and Cascades, where they talked about, oh, you're automatically going to learn what some of these rules would apply very early on. They say, we're not doing any of that. We're data people. We're paid a lot of money. They're going to basically hand pick which transformation rules they want to apply. All right, in these different stages. All right, so the first stage is just do simplification and normalization. And the idea here is like, I'm converting a logical tree to a logical tree. And these are like the things we talked about in Starburst. We're always going to want to do them. So you always want to do predicate pushdown, entry result pruning. Like if you have a subquery, like it says like select star from table where false. You know that subquery isn't going to produce any results. Just throw it out, ignore it, right? Subquery removal, we're not going to talk about that. And actually, I skipped that. Or actually, for Monday's class next week, when you read the chapter about transformations, I'm telling you not to read how they do subquery, because we're going to see how the Germans do it, which is the right way to do it. We'll cover that later. But outer joins, inner joins, all these things, right? So these are things you want to do very, very quickly in the very beginning, right? If for like really simple queries, like you can do this in milliseconds, less than that. Then there's a setup that they call the pre-exploration phase, where it is going to be, it's not going to be a cost-based search. It's more like you're going to set things up for getting ready to do the cost-based search, right? So if you know, again, trivial plans you throw away, normalization projections. One interesting thing they do is that if you start looking at your logical plans and you realize that you don't have the statistics you're going to need at that point, or when you actually want to do the cost-based search, right? Because then the cost model is being based on the statistics on the catalog. But if there's nothing in your catalog, they will actually stop the query optimizer right here, tell the data system, I don't have statistics I need, go run analyze right now. And then when analyze finishes, it then reverts control back to the query optimizer. MySQL does something sort of similar, not exactly go collect statistics, but if they have like a subquery, and rather than try to do the German style rewriting, they will take that subquery, actually go execute it. So block the query optimizer, go execute that subquery, which again recursively calls back into the optimizer, then run the query, then take whatever the output of that nested query and then feed that back into the query you're trying to optimize. That's not the right way to do it. That's wrong. We'll cover that later. But like, if you don't have statistics, telling you to go get statistics is actually a good idea. Databricks and Snowflake can't do this. And that's why I was saying that they do try to do late materialization of the query plan, because if you have a bunch of Parquet files in S3, you've never seen them before, no one's going to want to run analyze on that, because someone's got to pay for it. Snowflake doesn't want to pay for it. Customer doesn't want to pay for it. So they kind of defer some decisions later on. In SQL Server, because they're assuming, at least in this version of it, they're assuming running on the box that has the data, just go run analyze. So then now that feeds into the exploration phase. And this is where they're going to do the sort of the cost-based exploration of converting the logical expressions to physical expressions, as we showed before. But they're actually going to do this in multi-stages. So in the first stage, you're going to basically pre-declare what rules am I allowed to apply. Like for trivial things, select one will get thrown out here, but like, for chargeable queries, like select star from table where primary key equals this, right? So you do all those transformations at the very beginning. Then there's this sort of similar to the promise, there's this, when the stage finishes, you check to see how much time you still have left. If you still have time, and if you think you can find a better query plan, then you're allowed to go to the next stage. The next stage is basically the same thing it's, again, doing logical to physical transformations, and you're relying on the best physical plan you've seen in the previous stage to maybe truncate parts of the query search tree. But now you're allowed to apply more rules. In particular, you're allowed to actually start considering parallel query plans, right? With introducing exchange operators and having allowing multiple threads to scan the data. The query search in the optimizer is not parallel, but the query plan could be parallel. Then when that stage finishes, if you still think there could be a better improvements you could do, and how they estimate that's the black magic of this, right? Then you're allowed to go to the full plan. So some queries might not even go past the first stage, or they'll finish the first stage and be done. But like for really complex queries, they're going to go through all three stages. And then what they're doing is they're enabling more rules to be fired basically instead of setting the thing of like setting the promise to -0, they'll set it to something that actually is real, and then the optimizer is allowed to choose that rule to fire. And when that's done, they still have another stage where they do all the optimizations for whatever that they know the target engine that they're actually running on. So again, there's different flavors of SQL Server. There's like the parallel, like the data warehouse version. Now there's like Fabric or Synapse, a bunch of stuff like that. And we'll cover this later in the semester. But like, if I know I'm running a distributed version of SQL Server, then I take the single node plan that comes out of this third stage here, and then I basically do Cascades again on that. But now I introduce like the ship operators, the send and receive operators between the query plans across the different nodes. Yes.
So you said that the exploration stage is cost-based.
Yes. So like these are going to be all like, well, these are like, this is like if I don't have the thing I want, tell somebody, or join collapsing, like that you can do logically.
Yeah, I mean, but like, shouldn't it be like promise-based, like even the pre?
No. So promises tell you the order in which you apply the rules. The cost is going to tell you whether the plan's actually a good idea or not. You need both. But you can do Cascades without promises. It's just sometimes random, which is not good.
It's just Volcano.
Yeah, it's just Volcano. Yeah. But then you need the cost to figure out this is the best physical plan I could have. So you think of like the promises here, as I was saying, like it's my understanding of the way they describe it is like it's basically this file that says in the source code, okay, here's the rules that you're allowed to go apply, and then you're sort of passing that as input to the Cascade search. If you had promises, another way to do this is like you just say, here's the rules, set their promise to -infinity, so they never get even selected. And then when you get to this stage, if you want to include them, whatever stage you're looking at, then you set them to some real value. All right. So we talked about this first optimization the SQL Server does before, where basically instead of setting the timeout period, because again, like going back here, like this thing could run for potentially hours. Instead of setting it based on the wall clock, they set it based on the number of transformations that they've applied. So going back here, as they're going along, it's really most for this one, because these two phases, other than having to go run analyze, which is expensive, but like these two phases can be done pretty instantaneously. It's this one that's expensive. So like if I know that if I've applied 1,000 transformations and that's my budget, then you terminate there. And that's better than the wall clock time, because they said that this guarantees that the database system will always produce the same quality query plan for a given query, no matter whether the system is overloaded or underloaded. Right? Because it's a bad experience to say, if my system is super slow, and I now give it a query to optimize, and it's going to generate a crappy query plan because I was trying to get it out based on some time budget. The other cool thing they do is that in all my examples before, I showed like, oh, you start the memo table is completely empty. In SQL Server, they have a bunch of logic that says, or these heuristics they apply to pre-populate the memo table with things they think they should look at, right? And so, like, if simple queries, like if I doing a lookup on a primary key, I'll put that as the best physical expression that I have in my memo table ahead of time, so I don't even go and bother to explore that because I know that's the best thing for me. Again, it's throwing away computations, or it's a way to sort of short circuit the sort of raw exploration to find the thing that can be the best query plan. All right, quickly. I'm not going to talk about too much Greenplum because again we'll read a whole paper on this. But then, as I said, this is a standalone C++ implementation of Cascades. They originally wrote this for Greenplum and this thing called Hawk. Greenplum is a distributed version of Postgres that was a fork in the 2000s. Hawk was basically their version of Hive, of like SQL on top of MapReduce or Hadoop. And instead of building two different query optimizers for these systems, they took Orca, built it as a standalone service that can then take queries from both of them. So I think that's a really good idea. But as I said, they're one of the only ones that I know that can do the multi-threaded search. the way you use Orca is similar to how like you're setting up things in Calcite for project 1 is that they have this API or you give it a bunch of XML about what your catalog, stats, and logical plans look like, and then it does the search for you to do the physical plan. So this was open source in the 2010s, but this is complicated. So Pivotal was a spin out of EMC and VMware. Then it got bought back by VMware, and then Broadcom bought VMware, and then Broadcom made everything closed source in 2024. So even though the old version is there, it's not like the open source version is not actively maintained anymore, which is disappointing. But well, again, we'll cover this in more detail. Cockroach DB is another interesting one, custom written by Stoneberger's former student in 2018. As I said, what they do that's different than we've seen in SQL Server and in other implementations is that they have this custom DSL called OpGen. And the link here will take you to the GitHub page. Or actually, just sort of show you here. Like, so they have this DSL here where, like, here's the matching rules and everything, and then this is just going to get compiled into Go, and then linked into the program, right? So it's like the idea of like we saw in Volcano of like you're taking your rules and then code-genning C code that's much more faster than interpreting. As far as I know, Cascades originally didn't do that, but they had the same thing here in and Orca doesn't do this. They had this in Cockroach DB. But there's still there's a fallback mechanism if you can't express the logic you want in your rule all in their DSL. You can put in, or the transformation itself, they can put this in raw Go. All right, so quickly to finish up because I want quickly to about project 1. All right, so I like Cascades because again I think it's a cleaner. To me, I can think about what the query optimizer is actually doing. Now, obviously, the devil's in the details of how you implement the promises and determine the order rules get fired. How to do parallel search is also more complicated. But to me, this seems like a cleaner model of doing query optimization than in Starburst with the lollipops and stars and some of the other things we'll see later on. Now, the accuracy, of course, of the query plan, or the quality of the query plan is going to be highly dependent on the statistics and cost estimations. It just so happens that SQL Server has some of the best statistics and cost estimations. And so oftentimes when you look at comparisons of their query plans versus other systems, they do better, or they get the cardinality estimates to be more accurate. And so oftentimes their query plans could end up being better. But again, I think it's more tied, how much is you can attribute to the Cascade search they implemented versus the cost estimations, that remains to be seen. And the Germans do not care for the top-down search. They're all in on bottom-up search. And so we'll see how they do the joint enumeration in actually, I think next week. Okay? All right, any questions about Cascades? I'm going to quickly bang through project 1. Again, so for this one, the plan is you actually play with one of these query optimizers as a service. So we're using Apache Calcite. Calcite, we'll read this paper later in the semester. But there was a project called LucidDB out of Europe. It was a startup that failed. And then for whatever reason, they took out the query optimizer they built in LucidDB and made it an open source thing called Calcite. So the idea for you is you start playing with some of the rules you can use in Calcite to take queries, SQL queries, and see how the transformation rules that they apply to them can improve performance, right? So the two ways you're going to run the SQL query is going to be one through DuckDB in an optimized form, and then another one I think they have their own built-in engine in WAN, right? It's not built-in engine. But they have their own built-in engine in Calcite that you can run the queries as there and then compare them. You want to compare the results and see that they're correct. So we provided starter code to actually get Calcite up and running. It's in Java, so sorry. And again, the idea is that you're going to interact with this interface that that Calcite gives you to turn rules on and off, and obviously populate with statistics and so forth. Like the idea is that you want to start playing with Calcite and see how the queries change as Calcite applies those rules. And it's going to spit out SQL for you again. So you're not going to have a nice clean plan. We can talk about later on. We did try to actually use something to generate query plans and run those. It's called Substrate. That didn't work. So it's SQL to SQL, but you can still be able to see what it does. And so you got to make sure that when you run your queries on DuckDB, there's a flag called Disable Query Optimizer that basically takes almost the exact logical plan that the parser binder spits out and doesn't run the additional optimization on it. And that way you're running the queries that Calcite's giving you.
So the DuckDB will still have to choose the physical implementation
Yeah, but like it's a little translation of the SQL query coming in. It doesn't do any call-space search. All right, so the WAN wrote beautiful instructions for everyone to get started. Just follow those. Then beware of like stupid table name sensitivity issues. When the standard library rules do not include operation-specific rules. What's this again?
So, for example, we link you to like something called core rules. That is not all the rules. If you want rules for e-correlation, there'll be something else. So you have to look for that manually.
Yeah, so Calcite basically has grouping of rules similar to we saw in like SQL Server, and they're not all on by default. Thank you. Right. And then we can cover this later as well. Okay, so more instructions here. Again, it's in Java. We've tried to make it as easy as possible by giving you packaged up environments. And then you will submit things on Gradescope, and then Gradescope will basically run. And the idea is you want to check to see, the goal is to see whether you can have Calcite produce queries that are run as efficiently as the ones that DuckDB's query optimizer generates. Because the DuckDB query optimizer is actually really good because it's based on the German one. Right, we'll cover later. Okay? Again, I'm rushing through that, I apologize, but we can answer questions on the piazza. All right, so next class, we're gonna now talk about in more detail the transformations. We've been sort of like, oh yeah, commutativity, switching join order. Like we're talking about like, what are the actual transformations you want to apply to optimize your queries. And we're so cover everything in chapter 4 except for subqueries. So we'll spend a whole lecture on how to do that correctly. And then just like in this class, you do not need to submit a reading synopsis because it's reading the textbook, if you will, rather than a paper. Okay?
Matter of fact, hold the fuck. This is like that wood grain type of shit. Shout out to Blockhouse, my dogs. Catch one, big out, Mike Stroke, Gumby, all Dynamite. I'm not the one who be yapping up the weak ass rhymes. If you spit, if it don't rip through your mind with a sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep the Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like I make them hoes fuck quick and suck dick. Crown me as the thug in the gun. Shit, some niggas claiming never rapping is something. Don't push my button, yes you motherfuckers in front and you don't.